Welcome to Careless Coder. It's another dark and gloomy DOScember evening, so why not get stuck in and create one of these digital to analog converters for your PC. Motherfucker! So a couple of weeks ago in my video Fast Keycut Workflows for Beginners, we created this lovely little PCB for the Covox digital to analog converter. This was a little digital to analog converter that was created around 1987 up till the early 90s, which allowed you to actually play mod files from your XT, and even some games were supported. Now the workings are actually relatively simple, so we're going to explain that, but we're also going to explore how sound could be created. There are different technologies, we will explore just two of them, but yeah, it's a nice little piece of kit that you will have a lot of fun with. So let's jump in and first solder this bad boy up. The simplest DAC that we can make is the so-called N-weighted resistor DAC. It exists out of resistors that double in value. This is a 20k, then it becomes a 40k, 80k, 160k, 320k, 640k, 1280k, and finally 2.56 mega ohms. Now you can imagine that the absolute deviation of a smaller resistor and a large 2.56 mega ohm resistor is far bigger when you have a 1% deviation. These resistors need to be accurate. And also these resistors, if you want to scale up to 16 bits, need to continue multiplying. And resistors that large are hard to find if they're even created, especially with those tolerances. So what is a better solution? Well, that is the R2R resistor ladder. Now we see here that we only have two resistor values, a 10k and a 20k. So the 1% absolute deviation of these values is far less than with these very big mega ohm resistors, making it more accurate and scalable. Now we can simplify this resistor ladder schematic a bit more, so we can easily deduce it. This is how it looks when we simplify it. We have bit 1, which basically has two resistors in play, and we can simplify that even further. So we see the two resistors in this blue box, and we can simplify that by looking at this like this, and the voltage here is 5 volts. Because we're working with 5 volt TTL. And these resistors are technically in parallel. So you get a nice simple formula, 2R times Vref divided by 2R plus 2R, which becomes half the voltage reference. So 2.5 volts in this case. If we enable bit 2 and disable bit 0, then we have this block of resistors in play. We already simplified the bit 1 to this resistor network, and that basically becomes R because now they get in parallel, being that the voltage is 0 ohms. So we have these three resistors and the Vref that we carried on, Vref half the size of the previous one, so 2.5 volts, and then we have 2R times Vref divided by 2R plus 2R, because we have three resistors equaling that, and that becomes a quarter of the voltage. Now if we carry that on to bit 2, so you can probably already guess what is going to happen when we simplify this resistor network. It looks the same as before, and we end up actually with the exact same resistor network, halving the voltage again. And this will repeat for each stage in this resistor ladder. Now whether this is 8 bits, 16 bits or 24 bits, we keep halving the voltage, and this will scale unlike the N-weighted resistor DAC. So now that we know how it works, let's solder one up. I'm using some solder paste here, and I just tap the pads. A little goes a long way with these tiny 0806 components. I put down the first row of resistors. You don't need to be very accurate. As long as they make contact and you push them down properly, they will align in the oven. I did make a hand-soldered version, but for some reason I lost the footage. So here I'm putting down the second row of passive components, some resistors and a capacitor. And this really goes rather quickly. All the SMD components are on. Now put the pizza in the oven. This is an unmodified standard toaster oven. One that costs you about 30 euros. I set the temperature to 183 degrees centigrade. I did put a thermometer in there to actually see. And there it reflowed. You saw that happen. Nice. And it's looking nice. We can take out the pizza. Here I'm hand soldering a cheap Chinese knockoff of the CUI 3mm jack. I couldn't get my hands on the original versions. They're impossible to find, and this one the plastic feels very flimsy and I was afraid it would melt. And even on these I had to wait 4 weeks to get them in. Here I'm sliding on a DB25 male connector to edge solder it, and edge soldering is just flooding it with tin and making contact with the PCB. On the left we have the hand soldered version, and on the right we have the oven soldered versions. They look identical, so let's pick one up, put it in the LPT1, get a 3mm jack, stick it in the socket, stick the other end into an amplifier, and since I have a 486, I will start Galaxy Player 32 bits on LPT1. Yeah, it is working, but how does it generate sound? So let's create a very rudimentary digital oscillator. We start at 100 Hz, it's a COM file. I load DX with 3BC, that is my LPT port. Yours may be different. Look in your BIOS what your LPT port number is and substitute it here. Then I load AL with 0. Then I push that 0 out of the LPT port with the out statement. Then I increment AL, becoming 1. Then I jump back to sound, output it, increment it, output it, basically counting from 0 to 255, creating a sawtooth wave. So this annoying beep is a sawtooth wave, which runs at around 2800 Hz. This is the fastest that we can generate it with all the 255 steps. And hell, it's an annoying sound. So let's make a sine wave sound. Again, we load 3BC in DX, and I set the DI register to 0 because we're going to read a value from a sine table into AL and then output it to that parallel port. And if you have followed along with the Resistor bars episode of DOScember, then you know how to generate one of these sine tables. And in all intents and purposes, this is just the same. We will consecutively read bytes from this table and output it through the DAC, basically playing a sine wave. And when we reach the end of the table, we will reset the DI pointer to 0 again and just play the sine wave all over again. So we could see this as a very rudimentary sample that we just described ourselves. So this is a perfect 256 step sine wave. And as you can hear, the pitch is a bit lower than the triangle because we need to access memory, slowing it down. So in order to increase the pitch, we have to leave out certain steps. And that way we can shift the pitch up. And leaving steps out of a sample to upscale it will generate some of this typical aliasing that is well known to 8-bit samples when you speed them up. You can hear the clicking sound, that is some of that aliasing. Often you don't really notice the aliasing within a mix, and if you do, then it has that quintessential 80s sound. Let's take this idea of a sample a step further and create a PCM sample. Here I have a PCM sample, Hello 3, it's a 12 kHz sample. It's very noisy and crackly. I don't know what I did wrong in the conversion, but this code will demonstrate the PCM methodology. So here we set up a programmable interrupt timer that will be triggered 12,000 times a second. And every time it is triggered, it will call the sound interrupt handler that we set here. Here the frequency is set, and basically it's dividing that big number by the sample frequency. And this value should be 100, but I found out that 80 works better. This is probably because of some overhead in my interrupt routine. Now here I set DX again to my LPT port 3BC. DI is still our sample pointer, and the rest of the code is the same as the SINE code in a way. Now the sound function is triggered automatically by this PIT interrupt, and then every time this interrupt is triggered we will read a sample just like we did in the SINE, but I need to subtract 80 from it because PCM has a bias to 80, which is in the middle of a 256 value. And then we just push it out the LPT port, we fetch the new sample and either reset it when we are at the end of the table. Now very important is that we need to reset the timer interrupt, and that's what we do over here with the 20 pushing that into port 20. Then we pop everything from the stack and return from the interrupt. Simple. And we created a rudimentary PCM that sounds something like this. Oh my god. But it works. So this shows how PCM works. And to change pitches of samples, they basically change the timer interrupt. So if we change 80 to 70, my pitch will go up. I will start to sound a little like a chipmunk. And that's how sound is created in software. So there you have it, a very simple digital to analog converter with all passive components, which costs you around $5 in components. It's insane, especially knowing that the Covox sold for $79 US back in 1987. And I did reuse all the components that I had laying around, so that's why this 0.1 microfarad is not surface mounted, because I just simply didn't have one. And usually I have these CUI jacks in store, but I ran out. And getting components in 2021 seems to be a really big hassle. It took me 4 weeks to get these in from China, and they are a cheap knockoff. So I didn't dare to put them in the oven. I know that the originals bake perfectly fine, but I'm afraid, seeing how thin these are, that this would actually melt. So yeah, it's a nice piece of history. I got a couple made up now, so I could even do a stereo one. Cool. So I hope you learned something. I hope you get through these dark DOScember days, especially with fun little projects like these, and see you in the next one.